First, I would like to explain the basic properties of Gaussian analytic. So actually, the main target is Gaussian zeros of Gaussian analytic function, but maybe someone that do not know about this Gaussian analytic function, so let me explain some basic properties. And after that, I will explain our setting and the results. And 3, 4, 5 is the main topic of this talk. Oh, sorry, it takes time. Okay, so, but, it takes. So this is the main target of this talk. So AK is a deterministic sequence of complex numbers, and zeta k is the i.i.d, complex normal standard. And we consider this kind of power series, random power series. And then we are looking at the zeros of this function. And actually, this is a linear combination of the Gaussian random variables, so that this is a Gaussian process on some domain. But actually, the domain is the same as so you consider, so just remove this random part, then you get this deterministic function, power series. If you consider the radius of this, the convergence of this function, so the convergence circle of this analytic function, then it is the same. So for this, actually, for example, so this is the most important example called hyperbolic graph, and in this case, AK is constant 1. Then this hyperbolic graph has a covariance function like this. So it's called Segre kernel. Covariance function is, of course, defined by this way. And for Gaussian process, covariance kernel determines everything. So that this is very important kernel. And in this case, you just remove this zeta k, then this is the convergence radius is just 1. So that the zeros are sitting on this unit disk. So, of course, the zeros are random, so that we are considering a random point process on this disk. Okay, and also, so this is a covariance function. If you fix z, then this is complex normal with variance, something like this. So if you approach to the boundary, then this diverges, so that this random function oscillates very fast, and so that maybe you have many zeros near the boundary. Okay, and so this is a kind of a motivation, a little motivation of this talk, and so if you know about the autoregressive model, it is used in time series analysis, and this is called ARP. And so this part, so yt is a random variable, but depending on the past p values, and here you have noise. Then, so usually, so statistician uses this to consider the real data, and from real data they infer these coefficients. But anyway, this is just a stochastic discrete difference equations, and especially you take p equal 1, then it is called AR1, is a very simple equation, and you can solve this equation in this way. So you introduce the shift function like this. So Sx is just a right shift, and you rewrite this equation like this. Then you can solve this equation in this way. Then here, so Sk zeta is just a time shift by k. Then you have a Gaussian random variable here. So for each t, you have this kind of random power series, which is a stationary solution of this equation. Okay, so if you vary t, then you'll get the stationary graph. Actually, graph is a Gaussian analytic function. So this is a stationary graph-valued process. And we are just looking at the fixed t. then consider the zeros of this function. Of course, this is a stationary Gaussian graph-valued process, then the zeros also forms a stationary process. But anyway, yeah, okay. Okay, so this is a simulation, numerical simulation. On the left-hand side, this is for the hyperbolic graph. And right-hand side, I will come back to this later. But anyway, so for this, you can see many zeros on this disk. Actually, we are considering the infinite power series, so that for numerical simulation, we need to consider the approximated polynomial. So this is just a degree of 400. Then you have 400 point zeros inside. But here, of course, this is just approximation. The infinite series, for infinite series, all zeros inside the disk. But here, we have many zeros outside. And this blue one is inside the disk, and the red one is the outside the disk. So maybe half and half, half are inside and half are outside. And later I'll come back to this thing. Okay, so for graph, this is an analytic Gaussian process, so that there are many nice properties, and this is one of the important properties of this talk. So it's called the Edelman-Kosterland formula. And actually, so for zeros of graph, we can see the intensity or mean measure of the point process. And here, Sx is the covariance kernel of this, our analytic function. And you just take a logarithm and take Laplacian or a second derivative of this log. Then you will get one intensity function. This is a density of zeros of our process. Okay? For example, for this hyperbolic graph, the covariance kernel is Segre kernel. And you just consider this derivative, then you will get the hyperbolic volume. So it's called the hyperbolic graph. And there are many variants of this kind of thing, but the hyperbolic graph is very nice, one of the nice graph with some symmetry. There are three types of graphs which have nice symmetries. One is a hyperbolic graph, and one is planar, and one is elliptic or spherical. But anyway, so we are looking at this hyperbolic graph, and always sitting on the inside the disk. Okay. And next property is that so this is called the color with rigidity. So this is not the same one as but for analyticity, so we have a analyticity for the process. Then this kernel here is also analytic. And for the first variable, this is analytic. The second variable, anti-analytic, but anyway, anti-holomorphic. But anyway, you have very nice function here. And this function determines the off-diagonal part. So that if we know this information of this, so the diagonal part, then you will get the information of off-diagonal. And actually, as you saw, so the diagonal part is very closely related to the density of the zeros, so that we have this kind of rigidity. So x and y are graph on some domain, and you consider the one correlation function. Anyway, so this is a density function of zeros, rho x and rho y. And if they are the same, then if there exists some nice non-vanishing, non-random analytic function such that y and x times x, h times x is equal in rho. So that, of course, the zeros are also equal in rho. Because h is non-vanishing function, the zeros are preserved. So anyway, so if you know about the density function, then you know about the analytic function, so analytic graph. Okay, in this sense, the hyperbolic, so the graph on D, whose density of zeros is the hyperbolic volume like this, is essentially unique in law, which is nothing but the original hyperbolic graph. Okay. So this is one of the things. And as I told you that so this function, so the kernel, diagonal part of this kernel, determines everything. So that this is the evidence of that. And if you consider this kind of conditional kernel, so it is also called the Shirai complement. And you can define the inductively define this kind of multiple Shirai complement. Then the endpoint function of this zero is written like this. So here, Sx is the original covariance kernel, and you take this kind of kernel and take permanent. And the permanent is a signless version of the determinant. So usually for determinant, so this is a determinant. But if you remove this, then you get permanent. But anyway, so you compute the permanent and the determinant of this kernel and take a ratio. Then you will get the endpoint correlation function. So endpoint correlation function determines the point process completely. So that basically, if you know the kernel, so covariance kernel, then you have all information about the zeros. Okay.
Professor Shirai, is this conditional kernel have something with the producing kernel for a function that vanish?
Yeah, vanishing at alpha. Yes. Yeah, you're right. So it is also appeared in the Gaussian process setting. And for hyperbolic graph, there's a very nice result, a remarkable result by Perez and Virag. And actually, this zero-point process is determinantal with respect to this kind of very famous Bergman kernel. So once you know this result, actually, yesterday already for some explanation for determinant point process, but determinantal point process is something like a point process whose density is whose correlation function given by determinant. And so once you know this process is determinantal, then almost everything you can compute. But anyway, this is kind of a miracle. And actually, Perez and Virag computed this ratio. And there is a very miracle, kind of a miracle. And one of ingredients is Cauchy formula. Okay, anyway. Okay, and after that, so after the Perez-Virag work, there are several extensions. For example, Krishna pool extended to the matrix case. So GK is a P by P Genevre matrix. Genevre matrix means that each element is i.i.d. Complex Gaussian. And then you also have DBP for this zero. And also Forrester and Matsumoto and I consider the real version. And in this case, Paphian appears. And also Kato and I consider the Laurent series on the annuals. In this case, here we consider the Laurent series like this. And today I'd like to explain this result, which is the coefficient is not i.i.d, but stationary Gaussian process case. Okay, And in this paper, so we computed the expected number of points inside the ball. But what is the effect of the dependence? So that's the main topic of this talk. Okay, so this is our setting. And first we consider psi k. Psi k is a stationary, centered, complex Gaussian process with a covariance function gamma. So here we are considering a stationary process so that this covariance is given like this. So there is some function gamma, and covariance is just depend on the difference of the indices. And we assume that gamma 0 equal 1. This means that each marginal of this process is a standard normal, complex standard normal. And consider almost the same power series, but here psi k is not i.i.d, but dependent stationary process. Now, of course, if gamma k is a Kronecker delta, so this means that the gamma 0 is 1 and otherwise 0, then this is equal to the graph, hyperbolic graph, as I mentioned. The important remark is that all such this kind of graph, the convergence radius of this function is almost surely 1. So that point process, we are considering the point process inside the disk. So, okay. Okay, so what is the difference? So this Sx is the covariance kernel, and here the hyperbolic, the covariance kernel of hyperbolic graph. And if you put a dependence, then so there's a very nice special covariance structure. So this covariance is the product of the original hyperbolic graph. So this is the i.i.d case, and here the additional term here. And the first one is a Segei kernel, and second one is very closely related, spectral density. Actually, so g of z is the generating function of the covariance function, but except 0. So you remove 0. So, and here you consider z2, z and w. It is just 1 plus z of z plus complex conjugate of g of w. Okay. So later I will use a spectral measure so that here the definition of the spectral measure. Gamma k is a positive definite function. Then, so from the Helmholtz theorem, we have some probability measure here. And gamma k is written in terms of a Fourier transform like this. And if this spectral measure is absolutely continuous with respect to the Lebesgue measure, then this Radon-Nikodym derivative, so density is called the spectral density. Okay. Okay, so I will give you 3 very important examples. One is the simplest one, except i.i.d. And here it's called a one dependent case. The gamma k is 1 at k equals 0 and a at k equals plus minus 1, and otherwise 0. So it is very simple covariance kernel. And then g of z equals z, and z2 is something like this. Then you can see that this function, Fourier transform of this function is equal to gamma k. This means that this part is spectral density. So for this gamma k, we have a spectral density, something like this. So it is equal to 1 plus 2a cosine theta. In general, if z of z, so d of z is a, so this is the generating function of gamma, then so g2 if g of z is analytic in a neighborhood of D, then so this spectral density is given like this. So spectral density is almost equal to Z2. Okay. Okay, the next example is so-called Gaussian Markov. So in other words, so this is discrete Ornstein-Uhlenbeck process, and gamma n is something like this. Very complicated, but it comes from the i.i.d, the convolution of i.i.d and some sequence. Then the covariance kernel is this kind of exponential. In this case, z of z is something like this, and g2 is something like this. Then spectral density is equal to the Poisson kernel. But anyway, the important thing is that this is strictly positive.
Excuse me, the wall, now the Bergman times this GZ, can you give some reproducing kernel?
Maybe, yeah. Yeah. Okay, second one is a degenerated case. So you consider eta and zk, that they are i.i.d, and you define this kind of discrete Gaussian process. Then the covariance kernel is 1 and low. The 1 is at 0 and otherwise low. This is a degenerated case. And in this case, our graph is something like this. The linear combination of eta plus original hyperbolic graph. And then the spectral measure is not absolutely continuous in this case, and you have some singular part here. But otherwise, this part, second part, is almost the same as i.i.d case. Okay, so there are three examples. I explained three examples. And now we use a.d constraint formula for this process, for this graph. And actually, this is given, the expectation of the number of the zeros inside D is given by this formula. The first one is usually called the a.d constraint formula. And if you use the Stokes formula, then it is also written in terms of a contour integral. And also in our setting, so covariance kernel has a product structure. Then the first term is the i.i.d part. It is equal to this way. And also the second part is something like error term. Then we are focusing on this error term in this case. Then later, so we just consider the simplest case for D equals the disk of radius r. And then the first part, so this is an independent, so i.i.d part, i.i.d case part, r square over 1 minus r square, and plus something error here. So what happens for this error term? Okay, so we explain three examples. The first one is i.i.d, so this is just the first term. And the second example, so one dependent case. And actually, one dependent case, A should be less than or equal to 1/2, but here we are considering a strictly smaller than 1/2. Then the error term here is constant, order 1 term appears. And you can see that if A equals 1/2, then this diverges so that there something other appear. And the second case, for the Gaussian Markov case, this is also some constant, order 1 term. But anyway, both are negative. And as I told you, for the A equals 1/2 case, here you have another term appears. You have another term. So previous one is just order 1, but here we have a diverging term like this. And it is very closely related to the zeros of spectral density. Actually, so if A equals 1/2, then this is 1 plus cosine theta. This has zeros on the boundary. Sorry, on the circle. And second one, so this is a degenerated case. In this case also, we have some diverging part here. But anyway, depending on the structure of the spectral density, we have a different type of error term. Okay, so this is the first main result. So as you can see, you saw all error term is negative, but actually this is the case. For any for graph, and you put some dependence, then the error term is always negative. So that if you put dependence, then the number of zero decreases comparing with the i.i.d. case. The proof is very easy. Just use this formula. Then you get some negative term. Okay. Yeah, and error term is very closely related to the spectral measure, and so I want to see that part. And here, this is the error term. And usually, in the as you consider the residual analysis, then you can consider the pole of this integrand. And here, so we are considering the disk of radius r, but we just do a change of variable. Then you will get another function, similar function. It's called theta r here, and it is something like this. And if you have zeros of theta r, then this corresponds to the pole. And actually, so this theta 1, ei theta, is equal to the spectral density if there is a spectral density. So that the poles of the integrand of this integrand approach to the zeros of the spectral density. So the behavior of the zeros as r goes to 1 very heavily depend on the behavior of the number of zeros. Okay, so this is the first one. So the Gaussian Markov case, theta r can be written in this way. And the zero of this function is z equals 0. So here. But this doesn't depend on r. And then as r goes to 1, you just have a residue at z equals 0. So this pole doesn't move as r varies. But for one dependent case, you have different situation. So here maybe, yeah. So okay. Here for one dependent case, you have this function, so theta function. But theta function is something like this. So you have two zeros. One is inside the disk, and one is outside the disk. And the situation is something like this. And f is strictly less than 1/2. So these zeros stay away from the boundary. But if at a equals 1/2, this converges to the 1 point. That produce this diverging term. Otherwise, you just have a order 1 term. Okay, so this is the structure of this problem. Okay. Now we are going to the two-dependent case. It's a little bit different, but here you are considering this kind of covariance kernel, and 1 at 0, A at plus minus 1, and B at plus minus 2. But of course, for this gamma to be positive definite, AB belongs to this this domain. So here A and here B. So if AB inside this domain, then this gamma is positive definite. So that it becomes it defines a Gaussian analytic function. And there are several things. So one dependent case is B equals 0, so that corresponding to this line. And A equals 1/2 is here and here. So this part produces a diverging term. But in this case, you have many boundaries. So this red boundary and blue boundary, and the boundary of 2 boundaries. So this is green part. There are 4 regions. And depending on the region, you see the different behavior. The first 2 are the same as a one dependent case. But third one, so this corresponds to this green boundary here. In this case, you have different behavior. So here 1/2, but here 3/4. And idea is something like this. So in this case, so 2 dependent case, you have 4 zeros of this theta function. So case 1, so case 1 means the boundary, or this boundary. There are 4 zeros. The 2 are inside and the 2 are outside. But these 2 zeros are two zeros approaching to the 1 point, and here also approaching to the 1 point. But for the green case, so this case, so you have 4 zeros like this, and all zeros converging to the 1 point. This produces a power exponent 3/4. And you can extend this result, this idea, to the independent case. So in this case, so this is most degenerated case for the independent one, and the spectral density is something like this. Okay. And then, for example, for n equals 4, you have the 8 zeros or 8 poles of the integrand. And as r goes to 1, all points converging to the 1 point. And then you will get this type of exponent, 2n minus 1 over 2n. So if n equals 2, this is 3/4. Okay, anyway, so for finitely dependent case, we can see the following. This is a summary of this observation. If you have a finitely dependent stationary complex Gaussian process and the coefficients, and if the spectral density, so actually, so in that case, spectral density is a trigonometric function, and you consider the maximum of the multiplicity of the degeneracy. Then that capital N appears in this exponent. Okay, so this is a finitely dependent case situation. Okay. Okay, so far we saw this kind of thing. So actually, spectral measure plays a crucial role for the number of zeros. But for example, if n equals 30 or n equals 60, the zeros are very biased in some sense. So now we are, so far we have seen the number of zeros inside the disk, but maybe it is better to consider the sectorial domain or directional density. So that the next target is the directional density of these zeros. Okay, so before that, I'll explain a little bit. So now spectral density, spectral measure of this gamma is now, as I used, used before, as I used so delta before, but here we use f. And then xz itself has a spectral representation. So if you have a spectral representation like this, then the psi k also have a spectral representation. Something like this. So this is a Gaussian with independent increment Gaussian. So this is a stochastic representation of the psi k, discrete process psi k. And we use this formula to compute the xz, GAF, then you'll get this kind of representation. But anyway, by using this formula, then the covariance kernel is given like this. Okay, so we are looking at the diagonal part of this kernel, covariance kernel. Then the Poisson kernel appears here. And here also you have 1 minus r square. So if the point z approaching to the boundary, then the variance of this process diverges because of this term. But anyway, and then also we have a so different another representation of the covariance kernel, diagonal part. It is if the df spectral measure is absolutely continuous with respect to the Bergman measure, then using this density, Sx is given like this. So here, Bt is a Brownian, so complex Brownian motion on the disk, and starting at 0, z. And then, if z approaching to the boundary, this part is diverges. But if f has zeros, later I'll take a function. So here, f is a function on the circle, and for example, here 1 and here 0. Then starting the Brownian motion starting at z. So likely to hit this boundary. In this case, this expectation is close to 0, so that maybe so this covariance may be the order 1 term. Of course, if there is some cancelling here and here. But anyway, so this depends on so covariance variance. Depending on the boundary value, spectral density. Okay, so this is a simulation. So here, the density function, so spectral density is constant 1, corresponding to the i.i.d. case. But here, spectral density is something like this. This part is 1, and this part is 0. Then, you can see that there are many zeros around this boundary. But here, also you have many zeros, but these are all virtual zeros. Because, for example, if you consider, so we are considering the finite approximation so that there are all virtual zeros. So if you take 1 over 1 minus d, this is just an infinite series. But if you cut up to m, then this has many zeros on the boundary. So these boundaries are something like that. Okay. So in the limit, you cannot see the zeros on the boundary, but there are very few zeros on the left-hand side. Okay. Okay, actually, in this case, we can compute everything like this. And asymptotics is given like this. For phi is the angle, and phi is on this boundary, then the density is something like this. This part corresponds to i.i.d, and this part is error term. But this is order 1. But if you approaching to the boundary on this, along this line or this line, then the density decreases much. So here constant, but this constant is strictly less than 1. And if you consider this direction, then the density is order 1. So very few zeros on this side. Okay. So of course this is just an example, but for general case, if so you have a spectral measure df, and then and also PRS is a Poisson kernel, then directional density is given like this. Okay, and here you can see Poisson type integral, right? So for the denominator, you can see the usual Poisson integral, and in the numerator, you can see Poisson type integrals. Here, this is not Poisson itself, but the square of Poisson. So this part diverges as r goes to 1. So we need to consider the asymptotics of these quantities as r goes to 1. Actually, we can do that. And for example, for Poisson case, Poisson integral, this part is very famous one. So this approaching to the boundary value. So as r goes to 1, the Poisson integral so converges to the boundary value. But you can see the asymptotic expansion like this. So here, second term, so I is the integral operator like this, just the integral over minus pi to pi. So here is a local quantity, but here is a global quantity of the spectral density. And for the second Poisson type integral, this appears. But anyway, so maybe I should stop. The result is something like this. So for density, spectral density is strictly positive, then you get the i.i.d part minus order 1 term. But if you have so the density is 0, then the exponent decreases. Here 2 and here 1. And but this constant term, there is a second derivative. So if this vanishes, then we have different behavior. So if f phi and the second derivative vanishes, then you have a constant term. So this corresponds to this part. And finally, I just want to mention that, so here you have very few zeros. So if you can, you have a density, something like this, you can continue analytic. So you have analytic continuation along this arc. Actually, so if f is absolutely continuous with respect to the Drake measure, and define the I to be the complement of this support, then on this on this set you can continue this function, analytic function, almost surely. Actually, so if the Gaussian process is purely non-deterministic, the spectral measure is absolutely continuous, and its density is something like this. So this means that Fs is strictly positive. So this means that you cannot, you can't have an analytic continuation to the outside. So that this boundary is a natural boundary of this process. But anyway, we can discuss the analytic continuation. this is a summary. So we consider the zeros of Gaussian power series with dependent Gaussian coefficients. And if you have more dependence on the coefficients, then there are less zeros there are. And the future direction is, of course, we just consider, so far we consider the absolutely continuous case. But if you have a singular spectral measure, what happens? And also, we didn't discuss variance behavior, or CLT. And also, time evolution of the graph zeros is very important. Okay, thank you for your attention.
Thank you very much. So, are there any questions for Tomoyuki?
Can you encode your last result of this integral of the logarithm? It's a kind of Seger condition.
Yeah.
Can you encode or translate this result using Verbulski coefficients of the spectral density? So you have a function on the circle, you can compute its Verbulski coefficients, and can you translate at least your results using the behavior of Verbulski coefficients?
Yeah, I guess so, but so far I'm not so sure. I'm not so familiar with the various coefficients. So that, but anyway, the property of spectral density very correspond to the randomness of the discrete, so Gaussian process, so that you can encode something. Yeah.
Thank you. So you gave some formula for the expectation,
Yeah.
different kind of gamma.
Yeah.
Is there a formula for the variance?
Yeah, that's an important question. But
I mean, I want to.
yeah.
I think about hyper-uniformity.
Yeah, of course. Yeah, that is a very interesting problem. But for this case, we have a formula, but very complicated. Okay. So that still we haven't seen anything about that. So
and a formula with the S.
S means the covariance kernel.
Yes,
yeah. We can so by using a covariance kernel, we can represent the variance. But it is kind of a double integral, there are double integral, okay. But very complicated. So, but maybe something doable.
Yeah. And you have some idea about what kind of physics that correspond to this different choice of gamma?
Yeah, physics, yes. Yeah, maybe there are some physics related, but it's very closely related to so-called discrete Ornstein-Uhlenbeck process. The people are studying discrete Ornstein-Uhlenbeck. Yeah.
Okay. For which gamma?
So any gamma.
Any gamma.
Yeah. Usually people use i.i.d. Noise, so in the AR model. But if you change the i.i.d. with some dependent noise, then you'll get some discrete Ornstein-Uhlenbeck process. Okay. People are studying such a process. Yeah.
Thank you.
So no more questions. Let's thank the speaker again.
Yeah.